What if I told you that a single solar flare could plunge our planet into a technological dark age within minutes, wiping out power grids, disrupting GPS navigation, and crippling global communications networks that billions depend on daily? Imagine waking up tomorrow to find your smartphone useless, your bank account inaccessible, air traffic grounded worldwide, and hospitals operating on emergency generators, all triggered not by human conflict or cyber attack, but by a massive eruption of plasma from our own sun 93 million miles away. This isn't science fiction or doomsday speculation. It's a very real threat. Scientists have been warning about for decades, and by 2030, we're finally developing the sophisticated forecasting systems capable of predicting these cosmic storms. The Carrington event of 1859, the most powerful solar storm ever recorded, would cause catastrophic damage if it occurred today, potentially costing the global economy trillions of dollars and taking years to recover from. But thanks to unprecedented advances in artificial intelligence, quantum computing, and space-based monitoring networks being deployed right now, the year 2030 will mark a revolutionary turning point. Where humanity transitions from being passive victims of space weather to active defenders capable of anticipating solar eruptions days in advance and implementing protective measures before the first charged particle even leaves the sun's surface. This transformation represents a critical leap. Because unlike earthquakes or hurricanes that affect localized regions, solar storms threaten our entire planet simultaneously, targeting our technological backbone. The stakes couldn't be higher. A direct hit from an extreme solar flare could knock out satellites essential for weather forecasting, disable military communication systems, erase financial transaction records, and trigger cascading power grid failures that would leave entire continents without electricity for months or even years. Yet most people remain completely unaware of this existential threat lurking just beyond our atmosphere, largely because solar storms are invisible to the naked eye. But the scientific community knows better. They've been studying solar activity patterns for over a century, and their data reveals a disturbing truth. We're currently entering a period of heightened solar activity that will peak around 2025 and remain elevated through 2030, increasing the probability of eruptions. The good news is that we're no longer helpless observers. By 2030, we'll have deployed an unprecedented constellation of solar monitoring satellites, positioned at strategic points throughout the solar system, creating a three-dimensional surveillance network capable of tracking solar activity from multiple angles. These advanced spacecraft will be equipped with next-generation sensors that can detect subtle changes in the sun's magnetic field days before eruptions occur, providing crucial early warning that current systems simply cannot match. AI algorithms trained on decades of data will analyze these readings in real time. Identifying patterns and precursors that human analysts might miss while predicting the trajectory, intensity, and arrival time of solar storms with remarkable accuracy. This predictive capability represents a quantum leap from our current forecasting methods, which often provide only minutes or hours of warning, far too little time. The transformation happening between now and 2030 isn't just about better technology, it's about fundamentally rethinking how we approach space weather forecasting. But as our technological dependence has grown exponentially, governments and private companies are finally investing billions in comprehensive forecasting infrastructure. By 2030, we'll move beyond simply observing to actively predicting and mitigating effects through coordinated global response systems that trigger protective protocols. Power grid operators will receive automated alerts hours before solar particles arrive, allowing them to implement load-shedding procedures before damage occurs. Satellite operators will receive precise trajectory predictions, enabling them to reorient spacecraft and deploy protective shielding before radiation storms hit. Airline companies will receive real-time routing recommendations to avoid polar routes during solar events that could expose passengers to dangerous radiation levels. These automated protection systems will operate seamlessly in the background, invisible but essential for maintaining the infrastructure modern life depends upon. The development of these forecasting systems is one of the most important achievements of the decade because, unlike other threats, solar storms are an absolute certainty. Our sun operates on an 11-year activity cycle, and we're currently approaching the peak of solar cycle 25, which scientists predict will be more active than the previous. The economic case is compelling. A major storm today could cause damages between $2 and $3 trillion globally, with recovery taking years. By 2030, we'll have established the first truly comprehensive planetary defense system, marking a historic milestone in our evolution as a spacefaring civilization.
The technological revolution transforming space weather forecasting by 2030 extends far beyond improved satellite sensors and AI algorithms. It represents a fundamental reimagining of how we monitor, predict, and respond to solar activity through an integrated global network that combines space-based observation, ground-based monitoring, quantum computing analysis, and automated protection systems working in perfect harmony. At the heart of this transformation lies the deployment of next-generation solar observatories positioned at strategic locations throughout the inner solar system, creating a three-dimensional monitoring network that can track solar activity from multiple perspectives simultaneously. The Solar Orbiter mission, already providing unprecedented views of the Sun's polar regions, will be joined by an entire constellation of specialized spacecraft positioned at Lagrange points, solar orbit trajectories, and even on the far side of the Sun, locations that have been blind spots in our current monitoring capabilities. These advanced observatories will be equipped with hyperspectral imaging systems capable of detecting subtle changes in the Sun's magnetic field structure days before visible eruptions occur, providing the crucial early warning that current systems simply cannot deliver. But sensors alone aren't enough. The real breakthrough comes from how we process and analyze the massive volumes of data these spacecraft generate. By 2030, quantum computing will have matured sufficiently to handle the complex mathematical models required for accurate space weather prediction, solving problems that would take conventional supercomputers years to complete in mere hours. These quantum systems will run sophisticated magnetohydrodynamic simulations that model the Sun's internal dynamics with unprecedented precision, predicting not just when solar flares will occur, but exactly where they'll erupt, how powerful they'll be, and which direction the resulting coronal mass ejections will travel. This level of predictive accuracy represents a quantum leap from our current capabilities, where we often don't know if a solar eruption is Earth-directed until it's already en route, leaving us with minimal time to prepare. Artificial intelligence will play an equally crucial role in this forecasting revolution, with machine learning algorithms trained on decades of solar observation data identifying subtle patterns and precursors that human analysts might miss. These AI systems will continuously monitor solar activity 24 hours a day, automatically flagging concerning developments and generating probabilistic forecasts that update in real time as new data arrives. The combination of quantum computing power and AI pattern recognition will create a forecasting system capable of predicting major solar storms with up to 7 days of lead time, more than enough time to implement comprehensive protective measures across global infrastructure networks. This extended warning window transforms space weather from an unpredictable emergency into a manageable operational challenge, allowing power grid operators to implement gradual load reductions rather than emergency shutdowns. Satellite operators to execute carefully planned protection protocols rather than frantic last-minute maneuvers, and airlines to reroute flights proactively rather than grounding entire fleets reactively. The economic benefits of this predictive capability are staggering. Preventing even a single major solar storm from causing catastrophic damage could save trillions of dollars in avoided losses and recovery costs. But the true value extends beyond economics to national security and public safety. Military communication systems, emergency response networks, and critical healthcare infrastructure all depend on reliable satellite and power grid operations that would be vulnerable to severe space weather events. By 2030, automated protection systems will integrate directly with these critical networks, implementing defensive measures automatically when dangerous space weather is detected without requiring human intervention. Power transformers will be equipped with smart sensors that detect geomagnetically induced currents and automatically disconnect before damage occurs. Satellites will have onboard AI systems that can autonomously execute protection protocols when radiation levels exceed safe thresholds. Communication networks will have redundant routing systems that automatically switch to protected pathways when space weather threatens primary connections. This automation is crucial because space weather events can develop and strike with incredible speed, sometimes in less than 30 minutes from initial detection to impact, leaving no time for human decision-making in critical situations. The global coordination required to implement these comprehensive protection systems represents another major breakthrough happening between now and 2030. For decades, space weather monitoring has been fragmented across different countries and organizations with limited data sharing and inconsistent response protocols. But the growing recognition of space weather as a planetary-scale threat has driven unprecedented international cooperation, with major space agencies, research institutions, and private companies collaborating to create unified monitoring networks and standardized response procedures. The International Space Weather Initiative has already established frameworks for global data sharing and coordinated response, and by 2030, these frameworks will be fully operational with real-time information flowing seamlessly between monitoring centers worldwide. This global coordination extends to the private sector as well, with major technology companies, power utilities, and satellite operators participating in integrated response networks that ensure consistent protection across all critical infrastructure sectors. The economic incentives for this cooperation are powerful. No single company or country can afford to be left vulnerable while others protect themselves, creating natural pressure for universal participation in space weather defense systems. By 2030, we'll have established the first truly comprehensive planetary defense infrastructure against space weather, marking a historic milestone in humanity's technological evolution. This achievement represents more than just improved forecasting capabilities. It signifies our transition from passive observers of cosmic phenomena to active defenders of our technological civilization against threats from beyond our atmosphere. The systems being developed today will protect not just our current infrastructure, but enable the expansion of human activity into space itself, providing the forecasting capabilities necessary for safe lunar bases, Mars missions, and eventually permanent settlements on other worlds. As we become a truly spacefaring civilization, the ability to predict and mitigate space weather will be as essential as weather forecasting is for aviation and maritime operations today. The investment we're making in space weather forecasting infrastructure between now and 2030 will pay dividends for generations to come, ensuring that humanity's technological progress isn't derailed by cosmic events beyond our control. This transformation represents one of the most important technological achievements of our era, not because it's flashy or immediately visible to most people, but because it addresses a fundamental vulnerability that threatens everything we've built as a technological civilization. By 2030, we'll have turned the tide against space weather, transforming it from an existential threat into a manageable challenge that we can predict, prepare for, and overcome through the power of human ingenuity and technological innovation. The era of helplessness in the face of solar storms is ending, and a new era of planetary defense is beginning, right on schedule for 2030. If you found this exploration of space weather forecasting's revolutionary potential insightful and valuable, please subscribe to Tomorrow Intelligence for our ongoing coverage of breakthrough innovations reshaping our world. Like this video to help others discover the critical technologies protecting our planet from cosmic threats. Share with fellow science enthusiasts, technology professionals, and anyone who understands that humanity's future depends on our ability to predict and prepare for challenges from beyond our atmosphere. Hit the bell icon to receive notifications whenever we publish new content examining how artificial intelligence, quantum computing, and space technology converge to solve humanity's greatest challenges. Tomorrow Intelligence delivers deeply researched analysis separating genuine breakthroughs from overhyped claims, because understanding our technological future requires clarity, not clickbait. Join our community of forward-thinking innovators building the protected, prosperous world we all deserve.